just last year was declared the International Year of Quantum Science and Technology. Does anyone know why? 2025 was the International Year of Quantum Science and Technology, declared by the United Nations, not by me, mind you.
I think it was like 100 years or so after the beginning of quantum.
100 years after the beginning of quantum, exactly right. So in 1925 was the formulation of quantum mechanics. So I'm going to put the quantization of mechanics. Does anyone know the physicist who did this? Can anyone guess the physicist who did this?
Was it Albert Einstein?
Einstein is going to be a big part of the story, but not in this particular case. German physicist Werner Heisenberg in 1925. Okay, so it's been 100 years since this last year, but I'm going to go ahead and emphasize to you that just the following year, in 1926, there is another famous historical event. This one was due to another physicist, Schrödinger, who wasn't the first to formulate the quantization of mechanics, quantum mechanics, but he did two things. The first of which being wave mechanics. And I'm going to discuss what that is. We'll discuss it throughout the course. But I'm going to go ahead and declare another International Year of Quantum Science and Technology. So 100 years since 1926 since Schrödinger. So what did these folks do? They quantized mechanics. What does that mean? We have to back up the story a little bit. I'm going to take us back even further to the year 1900. In 1900, there's another scientist, physicist by the name of Max Planck, who wrote down something very strange. He wrote down for the first time energy quantization. The energy is proportional to the frequency of a system, and the proportionality constant is a new constant of nature, h, now known as Planck's constant. So this is the quantization of energy. And someone mentioned Einstein a little bit after Planck. The quantization of energy was seemingly a good idea. It was working, fixing some problems. In 1905, Albert Einstein introduced the quantization of something else. Does anyone know what Einstein quantized? For now, think of quantize as making discrete. So energy comes in discrete packets that's proportional to the frequency, sort of in integer multiples of some finite discrete amount. What did Einstein quantize in 1905? Light, exactly right. So this, we know particles of light as photons, and we can call this the quantization of light. Let me back you up a little bit more. Why were they quantizing energy and why were they quantizing light? Well, the state of physics was working very well until it wasn't working very well. So let's take our starting point with Newton in 1687 when he wrote his Principia. That gave us what we now call classical mechanics, but at the time it was just mechanics, how things move and how they respond to forces. So Newton had three laws. I'm going to write one of them for you. Newton's second law, F equals ma. And this is, for now, just mechanics. A few other notable events between these points in the history of physics that are relevant to the story and also just fun to know about. A little bit after Newton, gave us mechanics in the year 1824. French physicist Sadi Carnot wrote his in my worst French memoir. which gave us, for the first time, the second law of thermodynamics. Second law of thermodynamics. Why is this relevant in a course on quantum computing and quantum information science? Well, it does lead into the history of quantum mechanics with quantization. Max Planck was thinking about this and trying to fix some discrepancies. That's what led him to introduce this. But it's also very interesting. It fits with the notion of reversible processes. In this course, we're going to talk about computation a lot. And certain operations in computation, like AND, are irreversible. If you just know the output, you don't necessarily know the input. Very similar thing happens in heat engines. Carnot was studying thermodynamics at heat engines in the 1800s. And he showed qualitatively that reversible process is actually equivalent to the maximally efficient heat engine. So there's a connection between physics being reversible and the sort of efficiency of a physical system being maximal. There's going to be another very important link a few decades after Carnot in 1854. Physicist Clausius gave us for the first time entropy. How many of you have come across entropy in your studies before? If you haven't, don't worry, no one really knows what it means. He chose the name entropy to be as close as possible to the word energy. Okay? We hold energy near and dear to us in physics. Energy, entropy. So whereas the energy of a system of the universe stays constant, the entropy tends towards a maximum. Okay? So he gave us the first quantitative statement of the second law of thermodynamics. Shortly after, in 1865, and 1867, really for us, we care about 1867. Another famous physicist, Maxwell, did two things. In 1865, he wrote down Maxwell's equations for electromagnetism, which also influenced Planck's thinking, and is just a good thing to know in the history of physics. But in 1867, he gave us what we call today Maxwell's demon. Very interesting thought experiment, which you'll read about in the textbook, about the relationship between information, heat, as in heat engines, and entropy, which was introduced by Clausius in the previous decade. So this idea of Maxwell's demon we'll cover in detail, but for now I just want you to know this was the first time that there seemed to be a connection between these concepts. Information, which we tend to think about as abstract from the physical system, but also relating to heat and to entropy. Okay, so finally we're back to Planck in the year 1900. Physics was working well, there were some issues. He was trying to give sort of basis to the second law of thermodynamics, thinking about all these things that happened previously. And he tried a bunch of different things. In his own words, this hypothesis that he wrote down, the quantum hypothesis, was an act of desperation. Okay? So this is Planck's act of desperation. In the sense that he tried everything he could think of, and this was the last possible thing that worked. Okay? So physically, it's kind of a very strange thing. Mathematically, it's kind of a simple thing. It's sort of switching from a continuum to a discrete thing, switching from an integral to a summation, if you will. Okay? And that seemed to fix a lot of things. Einstein took the hypothesis, he quantized light, and that seemed to work very well also. And then, I'm not going to write it down, but in this period, Bohr also used this quantization hypothesis to come up with the Bohr model for the hydrogen atom, okay? For which he won the Nobel Prize. Einstein also won a Nobel Prize. The Bohr model for an atom worked amazing for hydrogen. It reproduced the spectrum of hydrogen perfectly. and it worked for precisely no other atoms, okay, so, except for hydrogen-like atoms. So the whole period between here, more or less, there's a lot going on, but is people realizing that, okay, the quantum hypothesis that we have before seemed to work well, but was no longer working well, okay? Heisenberg came in, and he quantized mechanics to try to fix that. Whereas Planck had an act of desperation, Heisenberg had an allergic reaction. He had hay fever, okay? And he went to an island off the North Sea where there's no vegetation. And while he was on that island, he did the following thing, which I want to write down to give you some intuition for what he did. So he started from this equation. X double dot plus f of x is equal to 0. Who could interpret for me what this equation is? Why is he starting from this? There's a hint on the board. He wants to quantize mechanics. So not just energy, not just light, but mechanics itself. So he's going to start from mechanics. Acceleration in a one-dimensional system is the second time derivative of position. So think of x as a position. X double dot plus some function of x is equal to 0. That's precisely Newton's second law. Okay? Acceleration being x double dot. I could rearrange, the force over the masses. Let's just write that as some function f of x. So that's his starting point. And what he does next is he solves this with a Fourier series. So he writes x as a function of time being equal to summation of alpha going from minus infinity to infinity, coefficient a alpha times some frequency e to the I alpha omega times time t. Okay? So nothing new yet, starting from classical mechanics, solves it with a Fourier series. Now he's going to borrow Planck's hypothesis in the sense that he's going to introduce some index now. So we're going to have some integer index, x sub n. Why the integer index? Well, remember the intuition. When Planck wrote this down, we're thinking of energy coming in discrete packets. So this is 1 unit of energy, 2 unit of energy, so on and so forth. So there's now this discrete index, x sub n, as a function of time. And where does this come into the right-hand side? A alpha becomes a function of the integer index n, as well as the frequency omega. So e to the I alpha omega of n times time t. So one index was so much fun that he decided to do it again. And he introduced a second index and a sort of the crazy step. So this is his sort of leap. What he did was no longer consider just one index n, but let me introduce another one, x, n, m. You can write it with a comma if you want, 2 independent integer indices, as a function of time being equal to the same summation. Now a alpha, a function of 2 indices, and the same thing for the frequency omega. Mathematically, what is an object with 2 indices? A line. Okay. Other ideas? A line in the sense that it has a slope and an intercept, 2 degrees of freedom, right? Think about other areas of mathematics. Matrix, exactly right. Matrix is a mathematical object with 2 indices, right? I specify the row and the column elements of the matrix. So this is matrix mechanics. After he did this, he studied products of these terms, and he discovered famously that they do not commute, right? So if I have another y, x times y would not necessarily be equal to y times x. Very different from Newtonian physics. So this was the sort of first discovery. And in his original paper, he actually didn't write it down in this clean of notation. It's a little bit messier if you look at it. but he gave it to his advisor, who was Born at the time. And while he was reading it on a train, he realized that, oh, this is actually what's going on. It's two independent indices. This is a matrix. And they wrote another paper about matrix mechanics. So in the following year, Schrödinger introduced wave mechanics to us. And how many people have seen the Schrödinger equation? Some of you. So I'll write it down. Perhaps more famous than what Heisenberg did. IH bar d psi dt being equal to some object h, which we call the Hamiltonian of the system, times this strange object psi, which we'll come to know and love as the wave function. So why is it called the wave function? Because it's a wave-like equation. And we're going to talk a lot about how to interpret what the wave function is. So the first thing was Schrödinger in 1926 wrote down this equation, and that seemed to be working very nicely. And then in another paper in the same year, he also showed the equivalence to matrix mechanics. So he showed that wave mechanics is equal to matrix mechanics. And we called it just today quantum mechanics. It's worth noting, although it perhaps wasn't completely original work physically speaking, but in 1932, a mathematician, John von Neumann, gave a mathematical foundation to what was going on and wrote a textbook, the title of which is The Mathematical Foundation of Quantum Mechanics, fittingly, which to this day is still very readable. And it's not going to be our textbook that we use, but if you're interested, especially in the history of physics, it's one worth checking out.